Okay, so what we're going to do is we're going to take a look at how to convert a regular expression, how to convert a deterministic finite automaton into a regular expression. So what I have here is I have a non-deterministic finite automaton, and I'm going to convert it to a regular expression. To do that, I'm first going to take this automaton and turn it into a generalized non-deterministic finite automaton. That has several properties which are listed in the book, but I'm just going to go ahead and do the conversion. So I've got a start state, which I'll call S, and then I'm going to add a new final state, which I'll call F, and I'm going to make that new final state accepting. And then the idea is that I'm going to add a transition from the start state to every other state in the automaton, and I'm going to add a transition from every other state in the automaton to the final state. Kind of like that. And then, so you can see now I've got two starting states. So what I'm going to do is I'm going to take the original starting state and make it a non-starting state and add an epsilon transition from the new starting state to the old starting state. But you can see I've also got a transition from the starting state to B, and this transition was never enabled in the old automaton, so I'm going to label it with the empty set. Keep in mind that in generalized non-deterministic finite automata, you label edges with regular expressions, and this regular expression right here represents the language containing no words, which means you can never follow this edge. Similarly, since the original state was not accepting, I'm going to take the new final state and label the edge between the new start state and the final state with an empty set to reflect the fact that that's impossible too. And then I'm going to take state B right here and make it non-accepting and make an epsilon transition down to F. So now I can get from B to F on an epsilon. Since A in the original automaton was not accepting, I'm going to label this with an empty set. And I think I've got everything labeled. The other thing that you need to have in a generalized non-deterministic finite automaton is an edge to and from every pair of states. So you can see state A here. I have an edge from A to B, and I have a state edge from A to F, and an edge from S to A. I don't want an edge from A back to S because that's one of the other rules, but you can check that out in the book. What I need is I need an edge from A to itself, and because that edge was not in the original automaton, I'm just going to label it with the empty set. Similarly, down here on B, since this edge was not in the original automaton, I'm just going to label it with the empty set too. All right, so the idea behind this method is that I'm going to take all the triangles of states in this graph, in this automaton, and I'm going to rip out one state in that triangle at a time. And when I rip out a state in a triangle, I'm going to relabel the remaining edges to include the behavior that I lost when I ripped out that state. I think that's easiest to see with an example. So I'm just going to pick a triangle, and this triangle is S to A, so that's the top edge of the triangle, so S to A. And then I'm going to go from S to B to A. So S to B to A. And remember, there's a loop from B back to itself. So I'm going to draw some circles here and a circle here. And then back over here in the original automaton, S to A was labeled with an epsilon. So that means that right here I'm going to take S to A and label it with an epsilon. S to B was labeled with the empty set. So I'm going to label S to B with the empty set. B to itself was labeled with the empty set. And B to A was labeled with a 0. So I'm going to label that with a 0. So what I do is I look at this triangle and I say, what's a regular expression that describes going from S to A through B? And then I'm going to take that regular expression and I'm going to union it with the regular expression that tells me how to get from S directly to A. So in this case, the regular expression for the path from S to B to A goes like this. I start in S, I take this transition labeled with an empty set. Now I'm in B, and I can repeat this transition 0 or more times. And then I go from B to A on a 0. So in regular expressions, that looks like empty set star, 0. So empty set star, and 0. So you may recall that there was an example in the book in which we talked about different properties of the empty set in combination with other regular expressions. The gist of it is that empty set star ends up being an epsilon. So I have empty set epsilon 0, and then the empty set concatenated onto any string is just the empty set. So what I end up with is that the regular expression for the bottom half of the triangle reduces down to just the empty set, which means that up here at the top of the triangle, I take epsilon union empty set and make that the new label on that edge. So I go back over here to the original automaton and I say, I'm about to rip B out of this automaton. When I do that, I need to change the label from S to A to include that path through B. And the regular expression that represents that path through B is just the empty set. And I figured out that empty set over here when I took empty set star 0, and reduced it to the empty set. So what I've done now is I've considered one of the triangles that has B as the bottom vertex and written down the regular expression that represents the behavior of that triangle when I rip B out of the automaton. I now need to do that for every other triangle that contains B. So let's take a look at another triangle that contains B. So the other triangle that contains B is a little harder to see, but it goes from A to itself, or from A to B back to A. So what I have over here is A goes to A, or A goes to, let me start over again. I have that A goes to A, or A goes to B, and then B goes back to A. The edge from A to A is labeled with an empty set, so A to A is labeled with the empty set. A to B is labeled with 1, B to itself is labeled with the empty set, B back to A is labeled with a 0. So I draw a regular expression that represents the bottom half of this triangle, and that ends up being 1 followed by 0 or more empty sets, followed by 0. So I have 1 followed by 0 or more empty sets, followed by 0. This goes to epsilon, so I get 1 epsilon 0, which is just 1 0. So I have empty set or 1 0 right there. So I take this empty set and replace it with or 1 0, because that's the effect of going down through B. The final one that I need to deal with is the possibility of going from S to F through B. So if I go from S to F, or if I go through B, then when I go from S to F, that's labeled with the empty set. When I go from S to B, that's labeled with the empty set. When I go from B to itself, that's labeled with the empty set. B to F is labeled with epsilon. So I end up with empty set star epsilon. As soon as I have an empty set here, I can just quit. So I get empty set or empty set, which, if you're following attention, you realize that unioning the empty set just gives you what you started with. So there's no change right here, because empty set union with empty set is just empty set. So at this point, I've considered every triangle that contains B, and I've added annotations to the, oh, I missed one, A to F through B. So A to F through B. All right, A to F is labeled with the empty set, A to B is labeled with 1, B to itself is labeled with the empty set, B to 1 is labeled, sorry, B to F is labeled with epsilon. So I get 1 empty set star epsilon, which is 1 epsilon epsilon, which is just 1. So I get empty set or 1 right here. And that represents the effect of going from A to F through B, but I'm about to kill off B, so I need this to represent the behavior that I'm about to remove. Okay, at this point, I've considered all the triangles that contain B, so I can rip B out of the automaton. So I delete B, and I delete every edge that went into or out of B, carefully leaving the other edges that don't involve B. Okay, so what I've got now is I've got a single automaton in which B is gone, and I've just got S and F and A. So what I'm going to do now is get rid of A, and I'm going to do that by considering all of the triangles that contain A and ripping A out and changing the regular expression to include the behavior that I'm going to lose. This one's pretty easy because, as you might be able to see, there's only one triangle that contains A. If I start at S and go to F, or if I start at S, go through A, and then go to F. So the triangle looks like start to finish, possibly through A, and I have a loop here on A. So from S to F is labeled with the empty set. From A to itself is, I'm sorry, I got that wrong. From S to F is indeed labeled with the empty set. From S to A is labeled with epsilon or the empty set, which is just epsilon. A to itself is labeled with 1, 0, because the empty set right there just goes away. A to F is labeled with just 1. So what I end up with is epsilon followed by 1, 0 star followed by 1. So I get epsilon followed by 1, 0 star followed by 1, which is just equal to 1, 0 star followed by 1. So I'm going to take that 1, 0 star followed by 1 and put it right there. So now the edge from S to F is labeled with empty set or 1, 0 star 1. This just goes away. So I have 1, 0 star 1 or empty set. I've now eliminated all the triangles that contain A, so I can delete A from the graph. So now this regular expression on the edge from S to F is the regular expression that represents the entire automaton. I can simplify it a little bit, and I just get 1, 0 star followed by 1. And that is it for that.